So EMF and internal resistance of an electric cell. Most of you did really well on this experiment. Let's cut straight to the analysis. This is the equation we're using. EMF equals the voltage, and in this case we're talking about the terminal PD. So this is our V. Okay, and that V, I like to do it this way, it just makes more sense. But that terminal PD will be equal to the energy coming in, the EMF, minus the energy lost across the internal resistance. And if we rearrange that, it looks like this. So if the current is varied through the circuit, the terminal potential difference will also vary. If a straight line graph of terminal potential difference on the y-axis is plotted with current on the x-axis, you can find EMF, and we can also find the internal resistance. So our independent variable would be the current that we are adjusting with our resistor here, and our dependent variable would be our potential difference, okay, which we measure with a voltmeter across there. Our controls, once again, would be our temperature. Okay, so we're assuming we're doing this under a constant temperature, and we are assuming that the resistance, internal resistance, is constant, okay, which we'll talk about later. Okay, so this is what our circuit looks like. Okay, a simple representation of the cell, and this is what our actual circuit looks like. And our ammeter is measuring the current, and a voltmeter is measuring the potential difference across the cell. So if we outline the analysis again, we end up with, okay, we have potential difference across the power supply equals the EMF minus the potential difference across the internal resistance, which is equal to current times the resistance of that internal resistor. Right, so if I now do this, if I try and linearize mx plus c, and what you should be able to see here clearly is that if we put the potential difference on the y-axis, as they ask here, plot a graph of V, and we put the current on the x-axis, which they ask for here, we are left with an intercept. So the EMF will be given by the intercept, and our gradient will be, okay, you can see that there, the gradient will be the internal resistance. So that's nice and easy. It's much easier than the last one, in fact. So we should have an intercept. Our line, you can see, because it's a minus gradient. You can see here we've got minus. So we're going to have a straight line that goes down like that, and our gradient is going to give us the resistance, and our intercept is going to give us the EMF. And that's what I needed to see in your basic analysis. Now, answering these questions, describe any patterns or trends shown in the graph. You should have found that you got a nice straight line with an intercept. Anomalies, again, refer to were there any points that didn't fit on the line. So did you get any anomalies, any weird points that didn't go on there? So that was very much up to you, so you need to look at your data and see if that was the case. Depending on how close to the line of best fit your points were, you could say that they were reliable or not. It says comment on the reliability of the results by analysing the spread of the points around the line of best fit. So if they're close, if they're all on the line of best fit, then you'd say it's reliable. We needed to see a gradient calculation and a value for resistance in ohms. It's super important that you give your values with the right units. A lot of you worked out your gradients, but then you didn't give me a value for R using the correct units. So what would I need for that? I need the gradient to be used and a value of R. Number 5. Then I needed maximum and minimum possible values. Now once again, for this you need your error bars, and that would be from your voltmeter readings. So just absolute error bar values. Now the increments, the absolute error on the voltmeter and ammeter is actually considerable if you were using the analog ones. So you could even actually have like horizontal and vertical error bars. Okay, now once you've got those, you would work out your maximum and minimum. So what does this give us in the end? I've just done a terrible job of doing that, but it should go near. Let me go back. Let me rewind and do that properly. Okay, that's a little bit better. So what you should end up with is a value for R, okay, from your first line, but then you need a maximum and minimum R. So what you do is you work out your maximum gradient, your minimum gradient, okay, and you work out the standard deviation. The same with your intercept. You can also now find a value for E, but you also now have a maximum and a minimum value for E. And what you do to work out the uncertainty is you use the largest deviation, or you can just subtract the minimum from the maximum and divide it by 2. Okay, so that's 2 ways to work out that uncertainty. So, number 6, which we've already outlined, use the y-intercept to work out the EMF of the cell, and also the y-intercepts to work out the maximum and minimum. So the maximum E and the minimum E from your intercepts. Comment on the precision of the result by analysing the uncertainty in the values. Obviously, the closer, the smaller these uncertainty values are, okay, the more reliable your results. So if you've got a value which is maybe 2%, 4%, if you go up to 10%, then we're talking about a less reliable result. In terms of the evaluation, there's all kinds of things you can think about. We have internal resistance is assumed to be constant, but as the power supply heats up, then you get a change in internal resistance. This would cause a slight curve. Okay, that might be something you've seen. What else? If we think of our circuit, there's always the old favourite. Our voltmeters, they don't have infinite resistance always. They draw current away from the circuit. So you could also say, or you could argue, the voltmeter has resistance. It's not infinite, and so also affects our results. And another really important one is the power supply is really old. So even though it says 12 volts, there's no way the power supplies actually now supply what's on the label. So you cannot guarantee the precision of the manufacturer's information. So how can we improve this? We can, again, use a switch. So we're only using the current to take measurements. So you switch it, you close the switch, take your measurements really quickly, and then you open the switch, and then that stops the circuit heating up. You can use a very high resistance voltmeter. Okay, the higher the resistance, the better. Okay. And maybe trying the experiment with a new cell. Okay, so you got a new battery, which is more likely to have the full voltage that you would expect.